first problem was they wanted you to find the sine and cosine of this degrees, okay, this angle, 120 degrees, which is the same thing as 2 pi over 3. Look at this angle over here, right? If we start at 0, okay, this is 0. Now I'm going to go up all the way to 120 degrees. There we go. Now, so like I showed you yesterday, this is 120 degrees, but at 120 degrees, that gives me a right triangle that's in this space called quadrant number 2, second quadrant, which is the upper left corner of your XY plane. And in this quadrant, 120 degrees gives me 60 degrees right triangle in quadrant 2. Does that make sense? Because here, this is 180 degrees, right? From here to here. And I know that this is 60 degrees because I took 180 minus 120, and I got 60 degrees. That gives me the right triangle that I need to work with. Now, to do the sine of this, I would be taking the red line, you understand? Divided by the hypotenuse. That hypotenuse, the black colored line, right? No matter where I go in this circle, because we call it the 1 unit circle, the length of this hypotenuse from the origin is always going to be equal to 1. Some of you still don't understand that. That means you barely understand the basics of trigonometry. So for those of you who don't even know that, you better go review from the very beginning. Okay, and then I take the distance, the height of the red line divided by the black line. So what is that height of my red line? Okay, well, this is a 60-degree right triangle. And like I showed you in the notes way back when, okay? Let's go to a 60-degree right triangle. This is 60 degrees here, okay? Now, the height again is 1. For this, okay, I know that my base of the triangle is going to be 1/2. That's the adjacent side. This height here, right, you can just use Pythagorean theorem, whatever. When you get that Pythagorean theorem, you do this. You get that the length of the opposite side or the height is the square root of 3 over 2. Do you understand? The square root of 3 over 2. So I will show you my solution to this problem, okay, that I did by hand. Okay, we're still number 1. That's the 120 degrees. This is the triangle I'm dealing with. Okay, so I'm going to pull out that right triangle like this. 60 degrees here. Here's my 1 for hypotenuse. This is my base, -1 divided by 2. This is my height that I just got, the square root of 3 over 2, which I just showed you right here. Yeah, square root of 3 over 2. So there we go. That is the length of the height. Take that, divided by 1, and you get the square root of 3 over 2. That's the answer there. To do the cosine, right? The cosine is going to be this base. Okay, so going back to the PowerPoint, if I went to my cosine slide, let's start this over. Let's go all the way to 120 degrees. Here we go. I'm looking at that red length divided by the hypotenuse. Make sense? So it's my base divided by the hypotenuse. What is the length of the red line, the base? Well, like in the notes, it is 1/2. But if you look carefully, okay, this is what some of you were confused about yesterday. I'm in this region of my XY plane. That red line is in a negative X direction. So there's going to be a negative value there. Understood? So when I'm doing the cosine, I have to make sure that's a -1/2. Okay, -1/2. And then -1/2 divided by 1 is -1/2. Done. We are now finished with number 1. So then now we're going to do the second question. So this time we're going to do the last question, which was an old test from I think June 2015 on your IGCC test, grade 10. So here's another pyramid, and someone will need to get this distance y, and then someone needs to get the angle between the sloping edge and the rectangular base of the pyramid, okay? So who is gonna do this one, which is harder, I think, a little bit. Oh, Olivia, yes, you may do it. Olivia, you wanna do it on the whiteboard or your screen?
Share screen.
Okay, go ahead, share your screen. Nice.
Can you see it?
I can see it. Let's see which side you use with Pythagorean theorem. Which side will you do? You need to get y first. Show us your work. Yeah. Okay. Let's see what you got.
Like
in the very beginning.
I draw it on here.
Okay.
Like just simple one, and this length is y, and you can see the bottom is like a rectangle, which is half of it is a right angle, and you can use Pythagorean theorem to like calculate, and the answer of DB is 5.7. Half of it is 2.85. We can again use the Pythagorean theorem to calculate the y, and which is 4.9.
Good. Correct. Very nice. Okay.
Do I need to?
Yeah, do part 2. Go ahead, finish it.
Then this one I use sine, and just you use this one to like calculate blah, 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 and which equals 54.7.
Can you show it? Olivia, show us in the picture. Oh, there. So that's angle ABE that she's solving for, guys. Okay. So good. That's correct. 54.7. Yeah, perfect.
Right.
Okay. Oh wow, that's good. So what you get in the very back? I think you just have one sign wrong on the last step. Okay.
Yes.
Yeah, a little bit.
Which one?
So the x to the power of 5 should be
Yes.
x to the power of 5 and then a minus 3x squared and then plus 1. That's the one sign that I think you missed. Yeah.
Oh, yes.
Yeah, because right, because the top part was already minus 3x squared plus 1 at the very beginning. So right.
So in the final answer, the x5 sine x plus or minus 3x.
At the final answer, it should be you have a sine of x multiplied all that in parentheses, x to the power of 5 and minus 3x squared and then plus 1. Does that make sense?
Yes.
Yeah. Okay. So let me go back to the whiteboard. What can you try to show us step by step? Let me see where you went wrong.
Oh.
Yeah, I know.
Oh.
Okay.
This one? Is it okay?
Okay, can you like rotate that so we don't look at it like from the side? All right, let's see where you went wrong. We're on number 6, you all. Class, I can ask anybody else to give feedback here where we think we did something wrong. Let's look at the first part of Sammy's thing. So, okay. He's got something divided by something, so you're going to have to use quotient rule. So that part is okay. All that jump times cosine of x, that's fine. He left the bottom part to the power of 2, that's fine. Now, the part I want to see where he did wrong is the next part. Is this a plus or a minus, Sammy? I can't read it. Maybe I'm wrong.
Which one?
This part I'm here. The very last fraction. Is that before the 3x squared? Is that a plus or minus? It's plus, right?
Yes. Sine x plus 3x.
Yeah, so
squared.
that part is the only thing that should be fixed. So it should be a minus. Does that make sense?
Oh,
Right, because
okay.
the 3x squared was always, remember the original part at the very beginning was already a minus 3x squared. So other than that,
Okay.
the whole thing is correct. Okay, so you only just
Okay.
again. A very good job. When it comes to the instantaneous change of a function, our goal is to describe how a function is changing. The difference between instantaneous change and average change is that we want to describe the change using only a single point rather than between 2 points. This can be used for things like the speed of a rocket a few minutes after launch, or possibly the instantaneous rate of change of a population. One problem we ran into is that when we normally describe something like the change of a function, we usually need 2 points to do it. This is so we can record both the change in the y direction and the x direction. If we are at a single point, it doesn't seem like we are changing in either direction. To see this, you might attempt to use a change formula for a single point. This unfortunately will give you 0 out of 0, which isn't useful for anything. Fortunately, there is a way we can find a change at a single point, and the secret is in using the average rate, but in a more clever way. Let's see how we can do it. To approximate the change at a single point, we choose a point along one other point, okay? This gives us 2 points. Using these 2 points, we find the value of the average rate of change between them. Now, rather than stopping there, we instead start moving the second point closer and closer. Each time we do this, we can record a new value for the average rate between them. Our hope is that as we find these new values, they will begin to get closer and possibly settle at some specific value. That's what we would call our limiting value. And it works great as an approximation to the instantaneous change of a function. So let's take a look at a simple example to see this in action. Here we have a function, and I want to know the instantaneous rate of change at this point here. I'll choose the point 4, 3, and then the other point I'll choose 6, 5. Now I can measure the average rate of change between these 2 points using my average rate formula. When I do, I get a value of 1. Now let's move that point a bit closer. If I measure the average rate now, I'll get a value of 1.5. Let's move it closer again. This time the value is going to be 1.8. As we continue to move the second point, we're getting different values for the rate of change. Even though they are changing, they seem to be getting closer to a limiting value. In fact, it appears they're getting closer to possibly the number 2. Let's move them closer to see if this is the case. After moving them really close together, our value for the average rate is now 1.99, and that's closer to 2. And it's even more evidence that the limiting value is indeed 2. Since we are looking at the average rate, that moving the point closer, 2 can be considered an approximation for the instantaneous rate of change of a function. In other words, it gives us a great way to describe how the function is changing at a single point, which is exactly what we want. Unfortunately, it is only an approximation, okay? It's just an approximation estimate, because we don't have any precisely saying where, or precisely the best way to say how close we are to the value of 2, okay? So the value could be 2.015 or 1.993. We can move these points closer together to gather more evidence, but it would be much better if we had an exact way of knowing that exact value, okay? So, a method for finding the limiting value exactly. Calculus has a problem for this. It's the first tool we need for many future problems, and that is the limit that we learned before, okay? But instead of finding a limit, we already know how to use the derivatives of a function at a point, remember? Anyways, to summarize, we can still get a very good idea of how the function is changing at a single point. We use our average rate of change, and then we move our points closer and closer together so we can find that limiting value, which is our instantaneous change at that point. Now, when we introduced calculus to physics, we talked about how Newton wondered about a falling body, such as the falling apple situation. He knew that if an object was dropped some short distance from rest, meaning with an initial velocity of 0, that velocity would necessarily increase in a negative direction every single instant until it hit the ground. He then asked, how can we calculate the velocity of the apple at any particular instant during the fall? That's called the instantaneous velocity. Now, Galileo, another scientist, had already discovered many years before that the distance traveled by a falling object is represented by the equation S of t, which is equal to 4.9 t squared. T is in seconds, and the distance is in meters. So Newton could easily use this law, okay, to calculate how far something would fall over a given interval of time. But this was not the problem at hand. Newton wanted to know something not about an interval of time, but he wanted to know about an instant in time, such as the velocity of the apple precisely 5 seconds after letting it fall. Well, just like we did when we first learned about the limits of a tangent line to a point on a curve, okay, let's make an approximation. Okay, so we learned about this before, right? When we learned about limits and tangents. So we can calculate average velocity by taking some distance traveled, okay, and dividing that by the time elapsed, which is equal to meters traveled over seconds traveled, meters per second. Now, using Galileo's equation, okay, we can express distance traveled as the difference between 2 points in this function. Say we use the distance traveled after 5 seconds, or the S of 5, and the distance traveled after 6 seconds, or S of 6. If we subtract S of 5 from S of 6, we are necessarily describing the distance traveled during the period from 5 to 6 seconds after being dropped. That will also mean that the time elapsed is 1 second. So we just evaluate the functions for these two endpoints and subtract, then divide by 1 second, and we get something like 53.9 meters per second. Just wait to see, yeah. Okay, so this is the average speed of the apple during that 1 second interval. However, we don't want average speed. We want the precise speed at a precise instant. So what we do, we're just like the way we brought the second point in the line closer to the first point until we got the best tangent line for the curve. Let's bring the end of this time interval closer and closer to 5 seconds. Okay? So let's bring that gap between the 5 and the 6 seconds closer. Okay? Decrease that distance. So one way we can start doing this is we can use, let's say, 5 and 5.1 to get the average velocity of this 0.10 second interval. And we get 49.49 meters per second. Then let's use, let's see, 5.015 to get the average velocity over 0.01 second interval. And we continue to get even narrower from there, okay? So if we were to continue in this manner, okay, we would see the average velocity get closer and closer to 49, right? Yes, so the instantaneous velocity of the apple precisely 5 seconds after being dropped must be 49 meters per second. This approach feels pretty similar to what we were doing with a tangent line. In fact, it's not just similar, it's exactly the same, okay? In both cases, we are performing derivatives, yeah? So we draw the graph of 4.9 t squared like this one. All we are doing is decreasing that time interval by bringing the second point closer and closer to the first point, right? We're bringing that second point closer to where the first point is at 5 seconds. And then we get a tangent line and the slope of the tangent line that gave us our instantaneous velocity, right? So this is equal to saying that the rate of change on the distance curve is distance over time, or velocity. This fact is no coincidence. It is the basis of why we do derivatives in the first place, like we have been learning.
When graphs have variation, derivatives can analyze the volume of a sphere. Came from integration. Math is a world of wonders, confusion and complex laws. That's how calculus helps us simplify. Why do we need calculus?